Hello everyone, this is the pre-recorded voice of Rob Barlow, here to tell you about recent developments in Raman scattering diagnostics for turbulent hydrocarbon flames. I'm very sorry I wasn't able to make it in person. Believe me, it's much nicer to give a presentation to a live audience than it is to talk to your computer in an empty room. So what I've done is to add in some extra animations to give the talk a little bit of bounce. And if the technology all works, then since this thing has already started, it should crank through all the way to the end. If you have any questions during the talk or after the talk, I don't know if I'm going to be available for live interactions, but if not, please send email to barlow@sandia.gov. I want to start by reminding you that I've never done any work on high pressure combustion. And most of the flames that we work on don't really even qualify as high Reynolds number, although we do try to push the Reynolds number as high as practical in the lab. What we've done is to focus on fundamentals of turbulence chemistry interaction in a progression of well-documented flames, to look at the coupling of turbulent flow, molecular transport, and chemistry, and to try to isolate the effects of turbulent chemistry interaction in flames that have increasing complexity. In this talk, basically, I'm going to tell you what we've done most recently to make our lives more complicated. The first part of the talk is on the investigation of multimode combustion in a pilot jet flame with inhomogeneous inlets. And the interesting thing about this burner from Sydney is that within the near field there's a very rapid transition from a stratified premixed mode of combustion to diffusion type flame structure. The next part of the talk will cover two different developments that we've been working on in extending Raman scattering to less friendly flames and to a wider range of hydrocarbons. And in the last part of the talk, I'll give a tip that may actually be useful for high pressure, high Reynolds number combustion, and that is how to extract the fully resolved scalar variance from under-resolved measurements. The motivation to study these jet flames with inhomogeneous inlets is that mixed mode combustion, that is combustion that has characteristics of both premixed flames and diffusion flames within the same combustor, occurs frequently in practical applications. Essentially, anytime you have a lifted flame or spray combustion, it's partially premixed, and there's a mixed mode of the flame structure that's present. An example of a laboratory scale flame that shows mixed mode combustion is the DLR model gas turbine combustor, and there's a very nice paper from last symposium from that group that combined PIV measurements, OH pLif in the red and acetone pLif in the blue to show that there are varying degrees of fuel air mixing moving into the reaction zone in this flame. And the problem with this combustor in terms of modeling is that the boundary conditions and flow field are rather complex. And it's important to test models first using burners that have relatively simple flame geometries and boundary conditions. This new piloted jet flame burner from Sydney University allows for investigation of mixed mode combustion in a burner geometry that's relatively simple and familiar. What they've done is to add a central 4 mm inner diameter tube within the main tube that can be recessed by variable distance. And the burner can be operated in two configurations. FJ refers to fuel coming through the central tube and air coming through the annulus, and FA refers to fuel coming through the annulus and air through the central tube. When fuel is injected through the central tube, there can be an enhancement of the flame stability by up to 40% in blow-off velocity if the recess distance is within an optimal range. So there's been quite a bit of work done and already published on a first series of flames that has air-to-fuel ratio of 2 and a stoichiometric pilot burning acetylene, hydrogen, and air with an adiabatic flame temperature of 2480, significantly higher than methane air. So we've also done, and what I'll present today, is a series of measurements that use a stoichiometric pilot with 5 gases to match both the composition and adiabatic equilibrium flame temperature of methane and air. But first, I want to remind you of the diagnostics that we use. At Sandia, we combine line-imaged Raman scattering, Rayleigh scattering, and CO laser-induced fluorescence with cross-planar OH-LIF imaging. For the Raman and Rayleigh measurements, we combine beams from 4 lasers to deliver about 1.8 joules per pulse total energy, and that allows us to measure temperature and all these major species with good precision and spatial resolution that's on the order of 100 microns, along a 6 millimeter segment of the beam, and that lets us measure the state of mixing, progress of reaction, and also gradients in the measured scalars. The OH cross-planar imaging allows us to determine the local flame normal direction, and from that we can estimate the 3D gradients and dissipation from the 1D measurement. I won't be reporting any information on these 3D measurements today. It'll all be just one-dimensional work. When we go through all of our calibration procedures and then go back and measure a simple flame, we can demonstrate that we can get very good results. And this shows a comparison between chemical calculations of a freely propagating premixed flame and our measurements on our best approximation of that type of flame at equivalence ratio of 0.73. And the blue shows the conditional mean, conditional on temperature, and the conditional RMS fluctuations as error bars. This table lists all of the flame conditions that have been measured, including a set of natural gas flames that were used in Sydney, the methane flames that were run at Sandia using the same velocities as those natural gas flames, and both sets of those flames were done with the 3-gas pilot and high adiabatic flame temperature in the pilot. And then the last group is this 5-gas piloted series of flames that were measured at Sandia, and within that we have 3 inhomogeneous flames with the FJ configuration and a recess distance of 75 millimeters, and those flames are at 50, 70, and 90% of blow off. And there are 2 flames with the other configurations. One is that with FJ fuel in the central jet, but with a recess distance of 300 millimeters, and this essentially burns like the homogeneous flame. It's not completely homogeneous. There are some fluctuations in mixture fraction at the exit, so we call that near homogeneous. And then there's an FA configuration with a 75 millimeter recess distance, but because the air jet is so high coming out of that small tube, there's very rapid mixing, and the mixture fractions is essentially flat at the or uniform at the exit, or very close to that. And both of those are at 70% of blow off. Lots and lots of data. There's just been a large paper submitted to Combustion Flame. In the downstream part, we have differences in the local extinction behavior, and then further upstream we have differences in the near field flame structure. And what I want to do for this talk is to focus on just 2 flames in the very near field and look at the differences and the evolution of flame structure within those 2 flames. 2 flames are each at 70% of the blow-off velocity, and at 1 diameter downstream of the jet exit they have very similar profiles in temperature, and also very similar profiles in the jet exit velocity, mean velocity, and turbulence intensity once those profiles are normalized by the bulk jet velocity, which is 80 meters per second in the case with 75 millimeter recess distance, and 59 meters per second in the case with 300 millimeter recess distance. But these 2 flames have very different exit profiles, or near exit profiles, in the mixture fraction, shown here at 1 diameter downstream. For mixture fraction, we're using Bilger's definition and defining unity as the condition with pure methane. So the stoichiometric mixture fraction is 0.55. So in the inhomogeneous case, we have a very peaked profile in the mean mixture fraction, whereas in the inhomogeneous case it's nearly flat. There is some asymmetry from side to side, and this is due to a slight offset in the centering of the central tube, which is difficult to center perfectly in these flames. But this asymmetry doesn't really affect our interpretation of the flame structure. The inhomogeneous flame also has minor asymmetry. You can see there's a slight dip to the leaner mixture fraction on the left side compared to the right side of the profile, but the symmetry is really pretty good. And what we want to focus in on now is what happens in the flame zone in these 2 different flames. So with the inhomogeneous flame, you can see that the mean mixture fraction is near stoichiometric within the flame zone here and here, where the peak temperature occurs, or peak in the temperature fluctuation occurs. And the fluctuations in mixture fraction in the flame zone are rather small. the hot peaks in the mixture fraction fluctuations occur in the interior of the jet, which also implies that the scalar dissipation is small within the flame zone. For the inhomogeneous case, this looks more like a conventional partially premixed diffusion type flame, like flame D, where the peak in the temperature fluctuation and peak in the mixture fraction fluctuation occur at the same place in the middle of the flame zone. Now let's go back to the scatter plots of temperature versus mixture fraction. And the first thing I want to show you is that there are some points that are affected by fluorescence interference, but these are really a small fraction of the samples, and fluorescence interference in these flames is a very minor problem. What we really want to focus on is the change in mixture fraction across the reaction zone. So the change in mixture fraction divided by change in temperature, and in the inhomogeneous flame there's nearly vertical trajectory. So this looks like premixed combustion or stratified premixed combustion, and most of the data points are actually along the floor here, going up to quite high mixture fractions, all the way up to about 0.7 on an instantaneous basis. And then for this near homogeneous case, there's a slightly or quite a bit smaller variation within the mixture fraction samples across the interior of jet, the cold samples, and then even smaller fluctuations in the mixture fraction entering the flame zone and lifting off the temperature floor. Then the slope is, or the dependence of mixture fraction or temperature on mixture fraction, nearly linear, and that slope is about minus 10 to the minus fourth inverse Kelvin. As we go downstream, in the near homogeneous case, the slope is essentially the same. It looks really similar, and in the inhomogeneous case, we're rapidly starting to pull into richer samples entering this reaction zone. Should point out that in the near homogeneous case, this looks very similar to what you would get in flame D, a slightly different starting value for the mixture fraction, but it's a classic partially premixed flame that behaves like a diffusion flame in that the strain rates are too high for any significant heat release in this premixed or in this fuel-rich part of the flame that would indicate heat release in a premixed sort of reaction zone. Here we compare scatter plots of species mass fraction versus mixture fraction in the two flames, and the samples have been color-coded for temperatures above 1400 Kelvin, so we can see what mixture fraction and samples are moving into the reaction zone. And in the inhomogeneous case, the scatter plots reinforce the picture that we've got a stratified premixed combustion sort of mode going on with near stoichiometric conditions, both lean and rich, moving toward the condition of the pilot. If we move further downstream, we again see that there's a very rapid pulling away toward richer samples of the mixture fractions that are moving into the reaction zone. Now what we want to do is to isolate the flame structure on an instantaneous basis using our line measurements. Here we compare instantaneous temperature profiles from each of the two flames, 25 shots in each flame, and each profile has been shifted to align the center temperature of 1200 Kelvin at the origin. And what we find is that in spite of the large difference in mixture fraction profiles for these flames, the temperature profiles are quite similar. And at this near exit location, they're not very strongly affected by turbulence. The fluctuations are limited really to the cool half of the flame for the most part. And these really look like flamelet type profiles. If we look at the mixture fraction, then in the near homogeneous flame, there's a very strong correlation between mixture fraction and temperature going through the reaction zone, and so aligning on temperature also aligns on mixture fraction, and with a value in the center of the flame of about 0.13 outside the flammability limit. Then looking down at the inhomogeneous case, we find that in the center of the reaction zone there are fluctuations in mixture fraction, but those are all within the flammability limits. And we see again that we've got samples coming from the lean side and from the rich side of stoichiometric and burning in a stratified combustion mode toward the stoichiometric or slightly higher than stoichiometric as measured conditions in the pilot. We can also look at the scalar dissipation, and here we're just looking at the radial contribution to scalar dissipation. And there's a caveat that we haven't measured the dissipation scales in the near field here, but based on previous work and similar flames, we expect that we're under-resolved. And so we're only using these dissipation measurements for qualitative comparisons. And what we find is that in the near homogeneous case, we have high dissipation in the middle of the reaction zone, and in the inhomogeneous case, we've confirmed that dissipation levels are very low within the reaction zone. The previous slide showed just 25 realizations from each flame, and here we're comparing histograms from 500 shots coming from each flame. And we confirm that the mixture fraction at 1200 Kelvin in the middle of the reaction zone in the inhomogeneous case with the 75 millimeter recess distance is centered near the stoichiometric condition and has both lean and rich of that stoichiometric condition. Whereas in the near homogeneous flame, the mixture fraction value in the middle of the reaction zone at 1200 Kelvin is too rich to burn. Now let's look over at the scalar dissipation. And here we see a distribution in scalar dissipation that is high within the flame for the inhomogeneous or near homogeneous case, and very low dissipation. Essentially all of the samples, or nearly all of the samples, are in the smallest bin centered on 0. Now what we want to do is look at the statistics of this flame structure metric that we mentioned in the scatter plots of temperature, which is the change in mixture fraction divided by the change in temperature. And we're using this macroscopic measurement across 1000 Kelvin because measuring the local mixture fraction dissipation in a premixed flame is sort of beyond what we can really do with our precision and resolution in these measurements. So this is sort of a macroscopic metric of the combustion mode, or the flame structure. And we see that in the near homogeneous case, we're dealing with a partially premixed diffusion flame with this value that's about -9 times 10 to the -5 inverse Kelvin. And in the inhomogeneous case, the optimally stabilized flame, we're looking at stratified premixed flamelets where the values of this flame structure metric are plus and minus, but centered near 0. Moving to 5 exit diameters downstream, there's obviously more turbulent fluctuation in these instantaneous profiles. The scalar dissipation in the near homogeneous case is significantly reduced already from what we saw at 1 diameter. And in the inhomogeneous flame, we're seeing a few intermittent high values of dissipation that correspond to these intermittent high gradients in the mixture fraction that's moving into the reaction zone. The histograms at exon D of 5 show that there's essentially no change in the LR300 case in the mixture fraction at 1200 K. But there's been a shift in the mixture fraction in the LR75 case over to something that's at the edge of the rich flammability limit, about 0.095 or so equivalence ratio, or mixture fraction. In terms of the scalar dissipation, we see that there's a lower dissipation in the LR300 case compared to that at exon D of 1. And in the LR75 flame, we're starting to see some high values, a few high values of the scalar dissipation. Considering the flame structure metric, in the LR300 case, we're still dealing with the same values, or same range of values that correspond to partially premixed diffusion flamelets. But now we have, in the LR75 case, a very broad distribution that goes all the way from the 0 premixed value up to values or in magnitude that are larger than what we find in the homogeneous or near homogeneous flame. So what we're seeing is that we're in the middle of a rapid transition from stratified premix mode of combustion toward a premixed or partially premixed diffusion mode of combustion in this LR75 flame. And what we want to do next is to look at how the flame structure changes as the magnitude of this flame structure metric increases. And to do that, we're going to coarsely bin our realizations according to the measured flame structure or metric for each realization. And we're going to include data from the -R side of the flame, which, if you recall, has a slightly richer mean mixture fraction. Slightly leaner mean mixture fraction, and will give us a bit more information at this end of the distribution. What we have here are results for the mass fractions of methane and CO2 conditioned on both temperature and the flame structure metric. So in the near homogeneous case, the LR300, we have a profile in temperature space of the CO2 that's concave downward and then turns up at the end. And these two lines correspond to the slightly lean and slightly rich stratified flames that we are sampling in the LR75 case. And those premix-like flames are concave upward and then, as a mirror image, dip down at the highest temperatures. In the Sandia 5, we're sampling a much broader distribution of the flame structure metric, and what we see is that there's a evolution as we increase the magnitude and that metric, going from the premixed sort of shape of the profile toward the partially premixed diffusion flame type of profile. As we move farther downstream to 10 diameters, the evolution in flame structure is essentially complete already by 10 diameters. The same sort of thing shows up in the results for water, CO, and hydrogen. In the premix type flame, there's a nearly linear correspondence between water and mass fraction and temperature, whereas the curve is slightly concave downward for the diffusion type flame. As we move toward richer samples within the reaction zone, we go to higher values of the CO peak mass fraction. And again, as we go down to XOND of 10, these profiles are essentially the same, and the evolution in flame structure that happens in this LR75 flame is nearly complete. We can gain some useful insights by considering strained laminar flame calculations. And sure, the turbulent flames are different. They're unsteady and they're in a high shear flow rather than a opposed flow. But still, we can consider two configurations. One is with flow against stoichiometric products, and that's relevant within near field before the pilot gases have been entrained. And the other is flow against air, and that's relevant after the pilot gases have been trained and somewhat farther downstream from this near field region. And what we've done is to vary the fuel side equivalence ratio and consider two strain rates, 100 inverseconds and 300 inverseconds. For the case with flow against stoichiometric products, we're limiting the profiles that are plotted here to temperatures that are below 2100 Kelvin. And this is similar to what we did with the turbulent flame data to eliminate the influence of the pilot gases on the profiles that we're looking at. And in the case with flow against air, we're limiting to conditions of mixture fraction greater than 0.05. So it's just the near stoichiometric and rich conditions that are plotted here. And what we see is that as we increase the fuel side equivalence ratio in either of these configurations, there's a similar trend in the shape of the CO2 mass fraction profile versus temperature to that which we saw in the turbulent flames. We can also gain some insight about the stabilization mechanisms in the turbulent flames by looking at the behavior of the integrated heat release rate versus fuel side equivalence ratio in the same laminar cases that we looked at in the previous slide. And let's first start with the case of configuration of flow against stoichiometric products. And what we see there is, in the red, is that there's only a really very narrow range in fuel side equivalence ratio that gives a high rate of heat release. And then that very quickly decays as you go to richer fuel side equivalence ratios. So that once you get to the point of the 2-to-1 air to methane mixture that is in the near homogeneous flame, then the heat release rate is down to 0. And what that means is that the near homogeneous case gets no benefit of heat release within the first few diameters until the product gases from the pilot are fully entrained. But the inhomogeneous flame, which has near stoichiometric reactants in the first few diameters, gets the full benefit of heat release from the stratified premixed reactions that occur in the near field. Now, looking at the case with flow against air, two things pop out. One is that once you get past a fuel side equivalence ratio of about 2, then the heat release rate is nearly independent of the fuel side equivalence ratio. Also, something that would be certainly expected is that if you increase as you increase the strain rate, the heat release rate also goes up until, of course, you get toward extinction. What's also plotted on here, along with the strain rates of 100 and 300 inverse seconds, is the line for 80% of the extinction strain rate, and that tracks actually quite close to the 300 inverse strain rate. And what this tells you is that you very quickly move from a situation where the stratified premixed flames are giving you more heat release in the near field to a situation where the strained partially premixed diffusion type flames are going to give more heat release. Let's look more closely at heat release in these strain laminar flames, considering just the configuration with flow against air. And what we have plotted here are profiles of temperature and volumetric heat release rate at the two different strain rates and at the listed values of the fuel side equivalence ratio. And let's first start with the stoichiometric flame. And what we see here at the lower strain rate is that there's quite a separation distance, more than 3 millimeters, between the location of the peak heat release and the location of peak temperature. And so this is really an independent premixed flame. There's a extended vertical region in mixture fraction where the temperature is increasing, and this corresponds to the burnout region of the premixed flame. And if you look at the trajectory of heat release in mixture fraction space, it runs through a loop that starts and finishes at the nominal stoichiometric value. And this loop is a characteristic of premixed combustion, and it results from differential diffusion within the premixed flame. Now let's look at the flame with 1.3 equivalence ratio on the fuel side, and here there's a smaller separation distance between the location of peak heat release and the peak temperature. It's less than 2 millimeters, and there's not any distinct or obvious vertical section corresponding to the burnout region for that flame. But if you look at the trajectory of the heat release in mixture fraction space, you still have a loop. So this is still essentially an independent premixed flame, so we have a double flame, but that loop closes off a little bit prematurely. So at the low end of the heat release, or the side of the heat release that's toward the air, you do have some diffusive communication with that air boundary condition. Now let's go to the higher strain rate, and what we see there is that there's no longer a loop. There's now there's been a shift in the location of peak heat release to a lower value of the mixture fraction, and it's significant to point out that all of these other values of the equivalence ratio have the peak heat release in essentially the same place. And this raises a question which I may not be qualified to answer, but perhaps some people in the audience would like to comment on this to each other, if not to me. Is this already a diffusion flame? When we go to high strain rates, does the premixed heat release or premixed combustion within the rich side of these flames already become irrelevant at this quite low value of the fuel side equivalence ratio? Okay, a quick summary on this new piloted burner. It's a new burner from Sydney University that adds a modification of a central tube inside the main tube, and that central tube can be recessed by variable distance upstream of the exit of the burner in order to vary the degree of fuel-air mixing at the exit. And if we inject fuel through the central tube and air through the annulus around it and recess by an optimal distance, we can enhance the flame stability by up to 40% higher blow-off velocity. The mechanism for this is that there's stratified premix combustion within the first few diameters, and the additional heat release from that augments the effect of the pilot. Going further downstream, there's a very rapid transition from this stratified premixed mode of combustion to a diffusion type mode of combustion, and that mixed mode combustion within that regime, we've proposed to use a metric of the change in mixture fraction divided by the change in temperature across some region of the flame to parameterize the flame structure. And we think this should be an interesting test case for models. If anyone is interested in the data and would like to get started, please contact Asad Masri or myself. And we have already released the data to a few people, and would be happy to release it to some more. So now let's move on to some diagnostics and look at the first of two extensions that we have been working on to bring Raman scattering into less friendly flames and into more complex hydrocarbon fuels. So first I want to remind you how we do the data analysis. And what I've shown here is a rather old picture, but it shows the image from a CCD array with no binning in either the spatial direction or the spectral direction. And this is an average image from a laminar partially premixed flame, 3 parts air, 1 part methane in the middle, flame A from the original piloted flame series. And as we move from the reactants or the air side into the fuel or partially premixed fuel, we move down in this image. On the air side we have oxygen, nitrogen, a little bit of water. On the fuel side we have oxygen, nitrogen because it's partially premixed, and some methane. And we see also some hydrogen, water, and some CO2, not quite yet. And this signal through out the middle here is fluorescence interference that happens on the fuel-rich side of stoichiometric. Now what we do in the lab to reduce the noise is to bin heavily on chip. And then we rely on theoretical spectra and integration of theoretical Raman spectra using a code from the University of Darmstadt to map out tables for the temperature-dependent response of the system to the molecules of interest, and also for crosstalk between the different Raman channels. And then we solve for species concentrations and mass fractions by iteratively solving a matrix or iterative matrix inversion that combines all of these calibration factors and accounts for all of the various crosstalks, including crosstalks from background luminosity and from fluorescence interference. Dealing with interference in this sort of approach, one defines an interference channel, and that's off on the left side or blue side of what we just saw in the spectrum, the C2 bands near 560 nanometers, and express the interference on each of the Raman channels as a temperature-dependent function of that 560 signal. This is easy to implement in the matrix inversion approach, and it's been successfully applied to a variety of flames that have relatively low levels of fluorescence interference. On the negative side, it's not possible to rigorously calibrate this sort of approach because the interference spectrum varies with local flame conditions, residence time, the fuel, and that means that it's always necessary to tune the interference corrections, and that process can be tedious, and it can be a tail-chasing exercise, especially for students that are not so experienced. And it's completely inadequate for flames that have very high levels of fluorescence interference. So what we want to do to extend the Raman scattering to flames that have high levels of fluorescence interference is to implement a technique of polarization, separation, and subtraction. Now, this has been done before by several groups. It's conceptually simple. The Raman scattering signals are strongly polarized. the fluorescence interference and flame luminosity are unpolarized. And so if we can simultaneously detect both orthogonal polarizations, or both components of the signal, we can remove the interference by subtraction. It also has the convenience of reducing the crosstalks, or the crosstalk corrections, or simplifying those corrections, because only the Q branch transitions remain significant. However, it's not simple to implement this as a quantitative single-shot technique for turbulent flames. Most of the demonstrations have had either poor spatial resolution or low precision. What we've done is to add a second detection system. And the illustration shows 3 cameras, but so far we've just got the Raman and Rayleigh cameras on this second system. And on the 2 sides of the table, we've got linear polarizers in each of the detection systems, and those are rotated to be orthogonal to each other. This slide illustrates how the technique works. It shows Raman spectra measured in a laminar methane air flame with volumetric ratio 3:1, and it includes the experimental vertical polarization spectrum, experimental horizontal polarization, the difference between the two, and then also a calculation from Ramsey's on what the signal should look like. And these are average spectra taken with no spectral binning. There is binning in the spatial direction, but not in the spectral direction. And the vertical blue lines show the regions of binning that we use or apply when we're actually doing measurements in turbulent flames. Now let's consider just the signal underneath this or within this CO region. And what you see here is there's almost no difference between the 2 signals with these 2 polarization components. And then the difference between those very effectively eliminates the interference part of the signal, which is most of the signal, giving a reasonably good agreement with the calculation from Ramsey's on what the CO signal should be at this position in the flame. And so this polarization, separation, and subtraction technique works quite well across most of the species, and there is an exception down here near the oxygen, where there's a very strongly polarized interference component that talks on to the oxygen signal, and then also onto where we're trying to measure CO2. And there is some indication in the literature that this may be a resonance-enhanced Raman scattering from C2, but we're not really sure. And there's some more work to be done to effectively find or subtract out this part of the interference. But for the most part, the technique works quite well. And these are results from a turbulent methane air flame with a methane to air ratio of 3. And results that were published by Gaetano Mignotti in the most recent symposium. And what we see are the scatter plots along with the blue conditional means, and the red calculation from Kemkin at a representative strain rate. And this turbulent flame has on the order of 20 times the interference levels as in the original flame D, but we can get quite reasonable results with still some scatter around the high interference region for many of the species. There's still troubles, as I mentioned, with oxygen, and this needs to have some more work to account for that extra interference. But generally, this is good progress. We have not yet applied this to a flame that we intend to use as or offer as a modeling target. So this is really a demonstration. Let's move on to the next diagnostic implementation, which is directed toward simultaneous detection of multiple hydrocarbon species. Our objective is to provide detailed scalar measurements in a series of partially premixed dimethyl ether air jet flames that's been developed by Jonathan Frank to be analogous to the original methane air piloted series. And it runs over this range of Reynolds numbers, which is slightly higher than that original series. Many years ago, Bob Dibble suggested that dimethyl ether would be a good flame for Raman scattering experiments because it's an oxygenated fuel, so it doesn't tend to soot a lot, and it's got some conveniences. It's kind of like propane. It comes as a liquid in the bottle, but it has a high enough vapor pressure so that it comes out of the bottle as a gas. So you don't have to use any liquid pumps or pre-vaporization hardware, and so that should be convenient. Well, that's not the whole story. So we've been working on DME for a while, and the first thing that we found out, working with Frederick Fust, who came as a PhD student from Darmstadt, and collected a bunch of data in laminar flames of a variety of small hydrocarbons, and then with particular focus was working on dimethyl ether. The thing he quickly found out is that you have to account for the main stable hydrocarbon intermediates in dimethyl ether flames if you're going to interpret the Raman and Rayleigh signals. And the reason is that they come in much higher concentrations, or mole fractions, than you get of intermediates in methane flames, where you can largely ignore them and sort of roll their contribution into the methane signal. Not so with dimethyl ether. And what Frederick did to get around this, since we didn't have any spectral information on the separate hydrocarbons with our setup, was to use laminar flames to essentially tabulate the effective cross-sections based on the laminar flame solutions and information that he was able to pull out from his own measurements and from the literature on the Raman and Rayleigh cross-sections of the individual hydrocarbons that were included as the intermediates in that calculation. And that was published in Combustion Flame. That technique was published in Combustion Flame in 2012. And applied to newer measurements of dimethyl ether flames that that Frederick made at Sandia and presented at the most recent symposium. But there are restrictions on that assumption, and what we wanted to do was be able to actually directly measure these other hydrocarbon intermediates within the DME flame and other small hydrocarbons. So we set off to measure the temperature-dependent Raman scattering spectra at temperatures up to about 900 Kelvin in heated flows, and this work was done by Isaac Akoto and is available in a Sandia report. At the same time, or in parallel, Frederick, and just published recently, was able to work up a Raman scattering interpretation of the, or Raman scattering measurements of acetylene in both laminar and turbulent flames. And I'll show you why that's a convenience, or why that's possible in a couple of slides. The spectral measurements at the low resolution that was done by Isaac Akoto turned out to be problematic for our interpretation of signals from turbulent flames. And so we had to go back and measure spectra at much higher resolution, up to similar temperatures, and that was done in collaboration with people at University of Texas. And most recently, Gaetano Mignotti is working on developing a dual resolution technique for measuring the CH stretch region of the Raman spectrum. First, let's look at some results from Frederick Fust, and these are results that are from the more recent set of measurements, but processed using his assumed flamelet structure approach that he developed as part of his thesis. And what this shows is species mole fractions in the DME flame D, and compares measurements at different downstream locations with laminar flame calculations at two different strain rates, and also with the assumptions of unity Lewis number versus multi-component transport. Now, the problem with the assumed flamelet structure is that we know it may not be valid in flames that had local extinction, and it may not be as accurate as we would like it to be, even at different locations in the flame, depending on what the role or what the importance of molecular diffusion is. It can be quite important in the near field and less so further downstream in terms of the way the mole fractions or mass fractions behave as a function of mixture fraction. These are measured Raman scattering spectra at low spectral resolution from Isaac Akoto's work. And the goal in making these measurements was originally to construct temperature-dependent spectral libraries and then solve for temperature and 12 species simultaneously using the matrix inversion process. And this sort of approach can work with acetylene, and Frederick Fust has just published some work on this, because the acetylene Raman scattering spectrum is separated from the other hydrocarbons. However, as you can see here, all the hydrocarbons have significant crosstalk or overlap in the CH stretch region of the spectrum, which is over here. and also across the region where we're trying to measure CO2, oxygen, and into the interference region. And this overlap with low resolution spectra makes it really problematic to isolate the separate hydrocarbons and measure them in an accurate way. So we've gone or went through a process of remeasuring all the spectra using much higher resolution spectrometer in collaboration with Utsav KC and Philip Varghese at University of Texas. And this is going to be coming or is in review for publication. And what you see here is an example for the spectrum of CH4 at various different temperatures measured in a heated flow system. Those high resolution spectra allow us to build spectral libraries that are more rigorous and will be more useful outside of just our system. But there's still significant overlap if we try to resolve those spectra with our original setup and the low spectral resolution that we have there. So what we realized was possible was that we could use an alternative configuration of this second detection system where we lift out the grating and final lens that are on the same mount and put in a higher resolution grating or high dispersion grating and a lens that brings the signal to the chip in a different orientation of the camera. And so in this dual resolution Raman scattering setup, we used the new detection or the second detection system to measure the spectrum only in the CH stretch region of the hydrocarbons, and then do all of the other species measurements with the original lower resolution setup that is on the left side of the table. And this slide compares the just the CH stretch region with those two different detection systems and shows that there's a much better separation of the features, spectral features, in these room temperature spectra when we use the higher dispersion grating in the second detection system. And it's something to point out is that the width in both cases, the width in pixels here is what it is because we're convolving narrow features of the actual Raman spectrum with the fat image of our laser beam. And because the magnification is the same on both sides, that spreading of the spectrum is the same in terms of pixels, but we've spread the CH stretch region across a much larger number of pixels in this higher resolution setup. Now we also show on here a spectral signature for formaldehyde, and the next slide will show some preliminary results on developing Raman scattering for formaldehyde detection. And that was discovered by accident when we were heating DME at very low flow rates, long residence time, and realized that we were starting to see some extra spectral signals as we went up in temperature, and we're able to identify those signals as methane and formaldehyde as pyrolysis products of the DME that was coming in contact with the high temperature heating elements. And we subsequently put in some heat transfer heat exchangers upstream so we could run the same pyrolysis temperature or same residence time and then cool the gases down a bit to get the formaldehyde Raman scattering spectrum over a couple of temperatures. And this is really preliminary work. It does not have an absolute calibration, but there is some possibility that we will be able to develop measurements by Raman scattering for formaldehyde, which would be very nice in these flames. So current work in progress, mostly by Gaetano, is to extrapolate these libraries to higher temperatures beyond what we'd actually measured and test those extrapolations by doing measurements in premixed flames and in opposed-flow partially premixed flames, comparing the results with calculations from Chemkin. And that, of course, opens up the issue of the accuracy of the mechanisms for dimethyl ether and differences among different mechanisms in their predicted species mole fractions. Now let's move on quickly to the last part of the talk, which is pretty short and may actually be useful for measurements in high Reynolds number, high pressure flames, where we really don't expect to be able to have the sort of spatial resolution, relative spatial resolution, that we have in the flames that I've just been describing. I'm going to start this by a short tutorial on length scales and velocity spectra in non-reacting turbulent flows, classic canonical non-reacting jet flow, and we want to define some terms. There's the outer scale, which is the half width of the mean velocity profile. And then we're going to do a hypothetical experiment on the centerline axial velocity in the far field using a hot wire. And so this is a trace of the velocity fluctuation. If we look at the autocorrelation, longitudinal autocorrelation from that time trace, we can define the integral scale, which is the area under the autocorrelation curve. And also the Taylor scale, which is the intersection of a parabola that's fit to the first part of the autocorrelation curve with the axis. And we also want to look at the model spectrum from Steve Pope, and that's been shown to be consistent with many experiments over a wide range of Reynolds numbers. And the parameter in the model is the Taylor scale Reynolds number. So if we normalize the wave number by the integral scale, then the spectra collapse at different Reynolds numbers. They collapse at the low wave number end of the spectrum. If we normalize the spectra using the Kolmogorov scale, then the various spectra at different Reynolds numbers collapse in the dissipation range and separate out as you go to higher Reynolds numbers and lower wave numbers. So we can also look at the cumulative energy and dissipation spectra from this model spectrum, and let's consider a low value of the Taylor Reynolds number and a reasonably high value of the Taylor Reynolds number. And to get the cumulative spectrum for the energy spectrum, we're going to start at high wave numbers and integrate down to low wave number to fill in the spectrum. And this is a three-dimensional spectrum. And for the dissipation spectrum, we're going to start at low wave numbers and integrate out to high wave numbers. And the point here is that if you have a high Reynolds number flow, then you have separation of scales. And at low Reynolds number flow, there's overlapping of scales. And this is what happens in most laboratory scale flames. We're really toward the lower end of these two Reynolds numbers. Another thing to point out is where the dissipation cutoff is, and that's defined in the theory as wave number times the Kolmogorov scale equal 1. Wave numbers are in radians, and so the corresponding length scale, or cutoff length scale, is 2 pi times the Kolmogorov scale. In gaseous flows, the Schmidt number is near unity, so the Batchelor scale for scalar fluctuations is comparable to the Kolmogorov scale. And from non-reacting jets, or experiments in non-reacting jets in the centerline far field, there are correlations that allow estimation of the Batchelor scale from the outer scale Reynolds number. And based on work by Guanghua Wang while he was at the University of Texas in Noel Clemens' group, we know that that same correlation works reasonably well in flames, at least in the downstream part of flames, as long as you use the local mean temperature to evaluate properties. The reason for going through that theory was to get you to these plots, which appeared in Guanghua Wang's Combustion and Flame paper in 2008. And what it shows is the effect of degrading the spatial resolution on the measured temperature variance and thermal dissipation based on theory and on two experiments. One of them is from me and Nathan on non-reacting passive scalar mixing, and the other is from Guanghua, where he applied high repetition rate Rayleigh measurements of the temperature in the DLR-A flame, looking at various different downstream locations in that flame on the center line. And what we see first is that there's good agreement between the theory and the measurements for a Taylor Reynolds number of 55, And then in the passive scalar mixing experiments, there's a good agreement with their quoted Taylor-Reynolds number of 180 between the measurements and the theory. And in both cases, if you consider the relative resolution such that a relative resolution of 1 means that you are fully resolving the thermal dissipation spectrum, then as you degrade that resolution, the dissipation measurement is degraded very rapidly, whereas the measurement of the variance doesn't degrade so quickly. And the higher the Reynolds number, the better your scale separation is, and the more quickly you lose the dissipation measurement, but are able to preserve the measurement of the variance. So in a high Reynolds number, high pressure experiment, we might have, say, a resolution requirement for full resolution of the dissipation spectrum that might be 10 microns. And maybe there's only a 200 micron resolution of the measurement. And what that leads to is that in the variance, you can get 90% if you happen to be at this Reynolds number. And that only gives you, same resolution will only give you 7% of the dissipation. So dissipation measurements are really out of the picture for high Reynolds number experiments. And the question becomes, how well can we actually determine the variance in a given point in a flame, or a given position in the flame? And that brings us to the punchline on how to estimate the fully resolved scalar variance from under-resolved measurements. And this might actually be useful for the sort of high Reynolds number, high pressure experiments that people here are interested in. And this comes from about 10 years ago in work in the piloted flame series, where we're looking at the mean and variance of the mixture fraction and applied a successive spatial filtering to the variance, and discovered that it degraded linearly, or nearly linearly, as the filter width was increased, and that allows for extrapolation backwards to a zero filter width and an estimation of the fully resolved scalar variance. I'd like to thank all of the collaborators and contributors to this talk, and also thank the organizers of this workshop for the invitation, which I am very sorry I could not actually make in person. So I'd be happy to remotely answer questions if we happen to have that set up.